So this is our last video of the class. I hope these have been helpful to you guys. In this video, since we don't have time to go through all of Chapter 9, we're just going to give you some of the highlights, some of the most important things that are covered in Chapter 9. You can always look through it in your textbook if you're interested in seeing more of what we would have covered with more time. One of the things is factorial, this notation with an exclamation point here. So if we look at this, first example here, this isn't just being really excited about the number 5. This is 5 factorial. And all that means is you start with the number 5, and then you do the next smallest number, the next smallest number, next smallest number until you get down to 1. So next smallest number after 5 is 4, and then times 3 times 2 times 1. And then you just multiply all those numbers together. So this one you could say that's 20 times 6. So 5 factorial equals 120. This is also built into your calculator. If you hit your math button right below alpha there, and then if you go over to PRB, factorial is used a lot in probability and counting. It will also be used in AP Calculus though. So the math button over to PRB, and then go down or hit the number 4, you've got that factorial button there. So let's see, I should type the number 5 first, and then math, you can hit the left arrow to PRB, and then hit 4. 5 factorial is 120. Okay. So of course, something like this, you could just type into your calculator. But a lot of times this would be a no calculator problem that it's actually pretty easy to do without a calculator. If you take a look at what this would be, you'd have 10 times 9 times 8 times 7 and so on. And then down here you would have 8 times 7 and so on. But you can see what would happen. The 8s would cancel out. The 7s would cancel out. And then 6, 5, 4, 3 all the way down would cancel out. So all you would be left with would be the 10 times 9, and so you would just have 90. All right, now let me back up a second here to this 0 factorial that I had highlighted. So obviously 0 doesn't fit this general definition of factorial that we have. So we had to just kind of make a special exception, specially define 0 factorial to be 1. You want to know that 0 factorial is not 0, it is 1. And I want to show you why, so that you know, but also because it'll help you with some of these problems that we're doing down here to see the logic of this proof. So what we're going to look at is we're going to look at n factorial over n. And if you write that out, so if we take any number, the next smallest number, to get to the next smallest number, you just subtract 1. So n minus 1, and then n minus 2, and so on. Well, if you look at that, just like we saw here, we can do some cancellation. We'll have those n's cancel out. And so we're left with n minus 1 times n minus 2, and so on. Well, what that is n minus 1 factorial. We're starting with n minus 1, then the next smaller number, the next smallest number. So this is n minus 1 factorial. So we know that n factorial divided by n equals n minus 1 factorial. So we could look at that for a specific number. We could say if n equals 1, then what we get is 1 factorial over 1. And then over here we'll have 1 minus 1 is 0. So we'll have 0 factorial there. Well, 1 factorial is just 1 divided by 1. This means that 0 factorial equals 1. So there's the proof. Not not that it's super important for you to know that proof or anything like that. It's just important for you to know 0 factorial does equal 1. And then what we're going to do a lot in here in an AP Calculus is do this kind of factorial cancellation with variables. And so if we take a look at this example here, well, if we're starting with 2n factorial, so we're going to have our first number is 2n. And then again, to get the next smallest number, you always subtract 1. To go from 5 to 4 to 3 to 2 to 1, you're subtracting 1 each time. So always subtract 1 each time. And then 2n minus 1 again would be 2n minus 2, and so on. And so then in the denominator, we start with 2n plus 2. And if we subtract 1, 2n plus 2 minus 1 is 2n plus 1. And then subtract the 1, we've got 2n, 2n minus 1, 2n minus 2, and so on. Again, we get lots of cancellation with these factorials. We've got the 2n's cancel out, the 2n minus 1's cancel out, 2n minus 2's, and these dots cancel out. And so we have nothing left in the numerator, so we've got the 1 there. What's left is in the denominator. Make sure it stays there. And so you've got 2n plus 2 times 2n plus 1 down there. And then we should just probably multiply that out. So we'd have 4n squared, 4n plus 2n, 6n's, and plus 2. So those fractions with factorials, just write them out and look for what cancels. And so these factorials often come up in what's called combinatorics, where you're doing counting problems, trying to count things. Now, the simplest level is when you have multiple things that you have to select like this, you're just going to multiply those numbers together. So 5 shirts, 3 pants, 2 hats. I often like to look at it as you've kind of got slots to fill in. So you have to fill in a slot with your shirt, you have to fill in a slot with your pants, and you have to fill in a slot with your hat. And then how many options do you have for each slot you're filling in? You've got 5 options here, 3 options there, 2 options there. And this is actually called the fundamental counting principle. You just take those different numbers of options and you multiply them together. So 15 times 2, you've got 30 different options. You could actually use that same principle for this problem here. There's going to be another way. There will be a formula that you could use, but you can actually still just use this fundamental counting principle. So if we have 8 athletes, and if we're only looking at gold, silver, and bronze, we're only looking at first, second, and third place. Nobody cares about the losers here, right? We're just interested in who's going to stand on the podium. And so we would say for first place, we have 8 different options. Theoretically, any of the different athletes could win first place. The thing that you would have to think about here is now second place, you wouldn't have 8 options anymore. You would say, all right, somebody already won first place, and no matter how good they are, they can't win both first and second place. So whoever won first place can't also get second place. So now we'd only have 7 options. And then we'd only have 6 options left for third place. But then we would still just multiply those together, fundamental counting principle. 56 times 6, that's going to be 336 options. So for both these problems, I actually do them the same way. Look at them as slots you have to fill in, how many options you have, multiply these together. There is also a formula for this, NPR. N is the total, and R is the ones that you're arranging in order. We're taking 3 of these and putting them in order first, second, third. So you could look at this as 8P3. And this is actually built into your calculator. I'll show you in a second. You could do this as well, and it does come out to be the same thing, but I would just do it that way. We're looking at these problems, by the way, because they can show up on the ACT. For those of you guys who will be taking the ACT, they have counting problems on them. So the one that's different is this one here where order doesn't matter. These things here, you can tell the difference between those slots, the order matter. Your shirt is very different from your pants, very different from a hat. Gold medal is very different from the bronze medal. The order matters. These different slots have to be kept separate. But here we have a problem where the order doesn't matter, where there's no difference. So here we still have 8 people, and then there's 3 of them that we're interested in. But we're just interested in who's going to get to see the movie. It doesn't matter which seat they're in. It doesn't matter who goes in first or so. We just want to see how many ways are there to pick or to choose or to select who gets those seats. So that's exactly what this formula right here, NCR, is for. You can think of the C as choose. So we're going to have 8 people, and we're going to choose 3 of them. You can see the formula here. You could work it out yourself if you want to. Or a nice thing is that it's built into your calculator, and the ACT is all calculator. So you would type the 8 first, and then go into your math menu, hit the left arrow over to PRB, and then this third choice. You can see they also have NPR in there if you do want to use that. But they've got this third choice here, NCR 8, NCR 3, 8, choose 3. And that'll be 56. So if you're looking at these counting problems, the important thing is to see whether order matters or not. If we don't care about the order, we've just got a bunch of people and we're picking a few of them, or some names in the hat, and you put a bunch of things, a bunch of names in a hat, and you're drawing a few of them, that's what NCR is for. If the order matters, if you can tell the difference between the things, you've got these other methods here. All right, so that's one thing that shows up in Chapter 9 is factorial and these counting problems. There's also some probability that we won't look at. The other part of Chapter 9 is sequences and series. So a sequence is just a list of numbers, and we often use A to represent them, and then the subscript N is just for the number in the term. So if we want the first 4 terms, sequences usually start with the first one. We usually don't start with 0. So we would say A sub 1 for the first term. And so this is called an explicit formula. You can just plug in the number term that you want into it. And so for the first term, I can just plug in 1. I can just say 5 times 3. And so the first term is 15. And then the second term would be A sub 2. We use subscripts to number things. So this is the second term of this sequence. And so I could just take n equals 2 and plug it into this formula. And so this time I'd have 5 times 3 squared. 3 squared is 9. So I would have 45. And then I can keep going for the third term. I'll have 5 times 3 cubed is 27. You can also probably see what the pattern would be here. This one is 135. And then A sub 4, 3 to the 4th power is 81. And so we get 405. So these are the first 4 terms. Sequences are often written in a list with commas, so you might often see this written as 15, comma, 45, comma, 135, comma, 405. And we're just using these subscripts to refer to each of these terms. The individual numbers are called the terms. And then if we have a formula like this, it's no problem to jump forward to another term. If we wanted the 10th term, A sub 10, we could just take 10 and plug it in. 5 times 3 to the 10th. And you definitely want a calculator for that. But if you use a calculator, that should come out to be 295,245. So that's sequences. And this is a special type of sequence called a geometric sequence. The way that we normally recognize geometric sequences is when they have this common multiplier here. So if you take a look at the pattern here, the terms of the sequence are, we're doing times 3 each time. Times 3 to get to that term, times 3, times 3 right here. As we go forward through the sequence, we're multiplying by 3 each time. That's why we had an exponential function there. Multiplying over and over again turns into an exponential pattern there. The way it's referred to, though, is that they have a common ratio. And so if you divide backwards in the sequence, if you take a look at 405 divided by 135, or 135 divided by 45, or 45 divided by 15. Each of these comes out to be the same number. It's a common ratio. The ratio of the fraction is the same. It's in common. Each of these fractions equals 3. And so this is a geometric sequence with a common ratio in R of 3. So a sequence is just a list of numbers. You're not necessarily doing anything with them. Then we have a series, which is a sum, which means that we're adding up all the numbers. And we often use sigma notation for this. So for sigma notation, we've got the general term here, the explicit formula, and then this tells us the first term and then the last term that we're adding up. So this tells us where to start and where to stop. So for this one here, we would start with k equals 2. It's not starting with the first term anymore, starting at 2. And so we would take 2 and plug it into this formula here. So negative 1 squared is positive. So we're just going to get positive 1. And then 2 times 2 is 4, plus 1 is 5. So we're going to have positive 1 times 5. We're just going to have 5 right there. And then we go to k equals 3 and plug that in. Well, now negative 1 cubed, 3 negatives, we're going to get a negative. And then 2 times 3 is 6, plus 1, we get 7. And then we keep going up to k equals 4, negative 1 to the 4th. Now we're back to positive. 2 times 4 is 8, plus 1, we get 9. And then k equals 5, negative 1 to the 5th. An odd number of negatives is going to be negative. And then 10 plus 1, we get 11. And then this is where we stop, because that's the number at the top there. So notice that this 5 is not the number of terms. We only have 4 numbers here. The 5 tells us the last number to plug into the formula right here. This says start at 2 and then keep going until you reach 5. And then sigma means sum. It's actually a Greek letter. It's a Greek letter S. I know it looks like a big E. That's the Greek letter S for sum. So if we want to compute something that has a sigma here, we have to actually add up all the numbers together. So that would be 14 minus 18. So that would be negative 4. Now, one interesting thing that you look at a lot in calculus is the notion of the infinite, looking at infinite things and seeing what you can do with it. And one interesting thing is that you actually can sometimes add up an infinite number of numbers. It's possible to do an infinite sum. So here we'll just look at infinite geometric sums. And it turns out there's a particular requirement. You have to have the absolute value of r being less than 1 for it to work. We'll look at why in just a minute. And to show you an infinite sum is possible, we'll take a look at this here. You can probably realize that this is going to be 0.3 repeating, which is 1/3. So it should make sense to us. Sometimes we could add up an infinite number of numbers. But let's go ahead and check out this formula that we've got right here and make sure that it works. Make sure that we do get 1/3 for this 0.3 repeating here. So formula, we need the first term. We've already got that. That's the 0.3. And we need to know R. We need to know what is the common ratio or what is the common multiplier. So you might be able to look at this and figure out what you're multiplying by each time. If you're not sure, just divide backwards. To figure out your R, you could take the second term and divide it by the first term. And if you look at 0.03 divided by 0.3, you're going to get 1/10, or 0.1, which makes sense. If you look at this to move the decimal one place to the left, you multiply by 0.1, or 1/10. So we're multiplying by 0.1 every time. That's our R. All right, so let's try this formula here. S sub infinity, the infinite sum. If we add up all these numbers till the end of time, never stopping, not just adding up some of them, but all of them, going forever. Start with our first term, 0.3. And then divided by 1 minus our R, 0.1. So we get 0.3 over 0.9. And then we could multiply the numerator and denominator by 10, or just kind of cancel out the decimals. That's the same thing as 3/9. And so we do get 1/3. So it matches what we know. Looks like the formula is working. And notice that our R was less than 1, so this works. We always want to check that the R actually is less than 1 before we use that formula. Also, a little side note here, so 0.3 repeating, we're very familiar with being 1/3. If you want to blow your mind a little bit, try this with 0.9 repeating. Try doing the same exact thing we did. Try looking at 0.9 plus 0.09, 0.009. Try looking at 0.9 repeating, and you'll actually find that the sum is 1. 0.9 repeating actually is the same thing as 1. That always blows some people's minds. You can try Googling it, looking at, there's lots of different proofs and reasons why that has to be the case, and this is one of them. If you use the infinite geometric sum, you'll get this fact. All right, just a couple last problems here. So if we take a look at this one, so this was the sequence that we looked at before, so we knew what the first few numbers were. We knew this was 15 and then 45, 135. We'll take a look at what's happening. The numbers are getting larger and larger and larger. So you're never going to be able to add up all of these. This is going to go to infinity. This one is not possible. Well, if you take a look at this, our common multiplier, common ratio is 3. You're multiplying by 3 every time. You can see in this formula right here, exponents mean multiplying over and over again. So you're doing times 3 times 3 times 3 over and over again. Your r is 3. Well, 3 is bigger than 1. And that's where this rule comes from, actually. If this is not the case, if the absolute value of r is not less than 1, you have a series where the numbers are not approaching 0. You have to add up an infinite number of numbers, you have to have each one, the individual terms, have to be approaching 0. They have to be getting smaller and smaller and smaller, closer to 0. Otherwise, the sum just blows up. So that's the reason for that rule there. Well, if we take a look at this one here, we can see that our r is a half. Again, the base of the exponential function, the thing that has the exponent on it, which you're multiplying by over and over again, is going to be your r. So r equals a half, and that is less than 1. So we can go ahead and use our formula there. So now notice that for the first term, we're going to use j equals 2 here. Even though it says a sub 1 in this formula right here, we're not going to plug in 1 into this formula here. We're going to use whatever is on the bottom of the sigma. So if we use j equals 2, we'll have 6 times a half squared. So that's 6 times a fourth. So 6/4, 3/2. And so then our infinite sum, we want 3/2, the first term, over 1 minus our r, 1 minus a half. So we want 3/2 over a half. And you might realize just that those denominators were canceled. Otherwise, of course, you can always say that dividing by a fraction is the same thing as multiplying by the reciprocal. And now we can definitely see those 2's cancel. And we just get 3. Kind of crazy that we can add up an infinite number of numbers and just get the whole number 3. So infinite sums aren't just for weird repeating decimals and fractions like a third. We can do all kinds of interesting stuff with infinite sums. That's going to be a whole chapter in AP Calculus, infinite series. All right, well, that's it. Again, I hope these videos have been helpful, and make sure you take advantage of this last week or so of this class to ask any last questions you have to make sure that you're ready for your next level of mathematics. Take care.